Hello everybody, welcome into the last lesson of graphing rational functions. So in the first lesson we talked about graphing rational functions which the degree of the numerator was less than the degree of the denominator. And then in the very last lesson we just did, we talked about graphing rational functions when the degree of the numerator equals the degree of the denominator. Now in this lesson we're going to talk about graphing rational functions when the degree of the numerator is greater than the degree of the denominator. So this one is actually probably the most interesting case. So here again to the right I have the general form of a rational function. If the degree of the numerator is greater than the degree of the denominator, there's a couple parts to this. If it's greater than the degree of the denominator by only 1 degree, there's no horizontal asymptote, but instead you have what's called a slant asymptote in the form of y equals mx plus b. And when we do this example, we'll discuss how you obtain that. If the degree of the numerator is greater than the degree of the denominator by more than 1 degree, then it doesn't have either horizontal or slant asymptote. So those are things to bear in mind. So let's go ahead and get started here. Alright, so let's talk about this function here. F of x equals 2x squared plus 3 divided by x minus 1. Okay, well, the degree of the numerator is greater than the degree of the denominator by exactly 1 degree. So that means we're not going to have a horizontal asymptote, but we're going to have what's called a slant asymptote. How would you find the slant asymptote? Well, the slant asymptote can be found by doing polynomial long division. If you take the numerator, divide it by the denominator, and ignore your remainder, you'll get your slant asymptote. So 2x squared plus 3 plus 0x plus 3, take that and divide it by x minus 1. So we'll do our polynomial long division. X goes into 2x squared how many times? It goes in 2x times. So then you get 2x squared minus 2x. Now subtract, let's see, so you should end up getting 2x plus 3. X goes into 2x how many times? It goes in twice. So then let's see, we get 2x minus 2. You would just end up with the remainder of 5. So your slant asymptote, you ignore the remainder when you do your polynomial long division. It'll only be everything but the remainder. So I actually have a slant asymptote of 2x plus 2. Y equals 2x plus 2. So we'll plot that. So the slant asymptote will be y equals 2x plus 2. So I'm going to plot that in red so we can see it. So let's plot our points here. Let's see. All right. Let's see, -1, that would give you 0. -2 would give you -2. -3 would give you -4. -4 would give you -6. -5 would give you -8. -6 would give you -10. So that looks crazy, but this is your slant asymptote, okay? Now, we still have the business of a vertical asymptote. So you plot your slant asymptote, and then you're going to find your vertical asymptote, which is going to simply be you set that x minus 1 in the denominator equal to 0. So x minus 1 equals 0. Well, that would give you x equals 1 to be your slant asymptote, to be your vertical asymptote. So let's go ahead and plot that. So for sure you're going to have a vertical asymptote, but instead of a vertical asymptote, you'll have, instead of a horizontal asymptote, you'll have a slant asymptote. So now we have plotted both the slant asymptote and the vertical asymptote. Now, let's start plotting some values here. What about when x equals 2? So let's plot f of 2. Well, that's going to be 2 times 4 plus 3 all over 2 minus 1, which would put me at 11. So I'm actually at 2. I'm going to be somewhere up here above the graph. So what about f of 3? Well, that would give me 2 times 9 plus 3 all over 3 minus 1, which would give me 21 over 2, which would still be 10.5. Basically, the closer I get, it's going to, this isn't entirely accurate, but your graph is going to do something like this. The slant asymptote along with the vertical asymptote helps to guide the shape of your curve. And yes, your graph can cross a slant asymptote, but just like a horizontal asymptote, it doesn't happen very often. Usually it stays within the boundaries. Now, what about if I go to the left of x equals 1, I pick 0? So what if I pick f of 0? Well, I would literally get 3 over negative 1, which would just give me a y value of negative 3. Now let's pick negative 1. Let's pick f of negative 1, which would end up giving me 2 plus 3 over negative 2, which would end up giving me negative 5 halves. That would end up making it negative 2.5 for my y value. So at, let's see, yeah, so 2 plus 3 is 5 divided by negative 2, I'd end up getting negative 2.5. And then, let's see, if I did negative 2, for f of negative 2, I'd end up getting 2 times 4 plus 3 all over negative 3, which would end up giving me 11 over negative 3, which would be back down to negative 3 2/3. So, you know, it's really weird. We rose again, but then we dropped again. So, negative 3 2/3. So, your curve's going to go a lot like this. So your curve is going to look a lot like this for your graph. It stays usually within the bounds of the slant asymptote and the vertical asymptote. They help guide the shape of the graph. So you're going to get something a lot like that for graphing 2x squared plus 3 divided by x minus 1. And I got more. what if I had negative x to the third divided by x squared plus 9? So I got f of x equals negative x to the third divided by x squared plus 9. Well, we need to find the slant asymptote, right? Because the degree of the numerator is greater than the degree of the denominator by exactly 1 degree. So we have the slant asymptote we're trying to figure out. That, of course, can be done by taking, let's see, that x to the third plus 0x squared plus 0x plus 0, dividing all that by that x squared plus 0x plus 9. All right, so x squared, this is actually negative x to the third, excuse me. X squared goes into negative x to the third how many times? It goes in negative x times, so this would end up giving you negative x to the third minus 0x squared minus 9x. So we'll subtract here. So that would be 0, 0. You'd end up getting 9x. So you'd have negative x with the remainder of 9x, which for your slant asymptote, you don't care about the remainder. You only care about what you got besides the remainder. So that means your slant asymptote is y equals negative x. That's exactly what you're going to get, is y equals negative x. So that is going to be y equals negative x for your slant asymptote. So let's go ahead and graph that. So still a 0 here. 1, I get negative 1. 2, I want to draw sufficient points so it's accurate. Negate it. There we go. So there's my slant asymptote of y equals negative x. Now let's try to find a vertical asymptote. So set that x squared plus 9 equal to 0. Well, you're not going to get any real solutions, right? So we have no vertical asymptote. We actually have no vertical asymptote. So we just literally got to work with the slant asymptote. So let's start plotting some values here. So at, let's see, when x is 0, well, you would literally get 0. It actually does touch the slant asymptote at that point, which is permissible. The only time it's not permissible to touch or cross an asymptote is if it's a vertical asymptote. But now let's put in x equals 1. Let's do some plotting here. So let's put in f of 1. That would end up giving me negative 1 over 1 plus 9, which would end up giving me a value of negative 1/10. So when x is 1, I'll be at negative 1/10, which is about right there. So now what about when x is 2? If I do 2, that would give me, of course, negative 8 all over 4 plus 9, which would end up giving me negative 8/13, which is a little over negative half. So I'll be about down there. Now what if I did f of 3? So f of 3, that would give me, let's see, negative 27 divided by 9 plus 9. So that'd be negative 27 over 18. which would be negative 3/2 or negative 1.5. So I'll have a y value of negative 1.5 here. Now, heck, let's do f of 4. So f of 4, that would end up giving me negative 64 divided by 16 plus 9, which would end up giving me negative 64 over 25, which would be negative 2 and 14/25, which would be over negative 2.5. So the right branch is starting to look very interesting here. And then let's go to the left. Let's go to x equals negative 1. If I put in negative 1 for x, that would actually give me positive 1 over 1 plus 9, which would give me a y value of positive 1/10. So at negative 1, I would get a positive value of 1/10. And then let's do negative 2. X equals negative 2, that would give me positive 8 over 4 plus 9, which would be 8/13. So that's a little over half. And then let's do negative 3. Let's do f of negative 3. You would end up getting positive 27 over 9 plus 9, which would be positive 27 over 18, which would be positive 1.5. So right there. And then let's do negative 4. So let's do f of negative 4. Well, that would give me positive 64 over 16 plus 9, which would give me 64 over 25, which would end up giving me 2 and 14/25. Should be about right there. So we see the way the curve's going to go. It rides the asymptote on either side. It stays along this slant asymptote of y equals negative x, and it does a really cool curve. And it crosses the asymptote at 0, 0, which is actually kind of cool. So you get this really cool graph here. Making sure y'all could see it. Okay. Now, let's do something here. What if I had x to the 4th divided by x squared minus 1? So now I have f of x equals x to the 4th divided by x squared minus 1. Well, it is true now that the degree of the numerator is greater than the degree of the denominator. That much is true, but it's greater than that. It's greater by more than 1 degree. If it's more than 1 degree, you have no slant asymptote even, no horizontal or slant asymptote. Because the degree of the numerator is greater than the degree of the denominator by more than 1 degree, you have no horizontal or slant asymptote. Now we can hope for vertical asymptotes. Let's do, for a vertical asymptote, we'll just set that x squared minus 1 equal to 0, which would give you x equals both plus and minus 1, right? Sorry, I just got a very important message. But anyway, you have your vertical asymptotes where x equals both positive 1 and negative 1. So I'm just going to plot the two of those real quick. So it's going to be very interesting not having either a horizontal or a vertical asymptote. You just have two, a horizontal or slant asymptote. You just have two verticals. So let's go ahead and start plotting some points. Let's go to the right of x equals 1. And really, you could kill two birds with one stone since both powers in the numerator and denominator are even. You could do actually f of both plus and minus 2. Which would actually end up giving you, in either case, 16 over 4 minus 1, which would give you 16 thirds, right? 16 thirds, as we know, is going to be 5 and 1/3. So when x equals either plus or minus 2, you'll get a y value of 5 and 1/3. Okay. Now let's do plus and minus 3. You're going to end up having, of course, then you would have 81 over 9 minus 1, which would be 81/8, which would be 10 and 1/8. So at 3, you're all the way to about, we'll say there. And same with a negative 3. So what if we get in between 1 and 2? Why don't we pick like 1.5? And really, this should actually work again for both plus and minus 3/2. So it's going to get a little hairy for a second. So let's see, 3/2 of the 4th power, that's going to be 81 over 16. All that divided by 9/4 minus 1, which would be 4/4. So that would be 81 over 16 divided by 5/4, which would end up giving you 81/16 times 4 over 5, which would end up giving you 81/20, which would end up being 4 and 1/20. So 1.5, both positive and negative, you're at 4 and 1/20. So really, if we can see the pattern here, it's just really doing a weird thing where it starts near the asymptote, and then once you get immediately past x equals 1, it's really taking off. And same in the negative direction. It's going to do the same. It's going to ride your asymptotes. No, I know some of you are going to laugh at that. He's really riding my asymptotes. I guess we could have some humor at this, but looks roughly like that. Starts strong near the asymptote, then really takes off. And this continues downward and downward, of course, infinitely close to the vertical asymptote without actually reaching it. I guess I could extend it all the way down. Why not? Just so you get a full representation. Now, what's going to be interesting is when we get in between -1 and 1. That's because we're actually going to have a third piece of this. So let's pick 0. I think it's obvious at 0 you'll get 0, so that much is easy. Now why don't we pick plus and minus 1/2? F of plus and minus 1/2 on both, okay? 1/2 to the 4th power, that's going to be 1/16 all over, let's see, 1/2 to the 2nd, that's 1/4, then minus 4/4. Well, that's going to give you 1/16 divided by -3/4, which would end up giving you 1/16 times -4/3, which would end up giving you -1/12. So you'll get a y value of -1/12 for each x value of positive and -1/2. So it's going to be like an upside down parabola close to the asymptotes on either side in between. So you got a very funny graph here for f of x equals x to the 4th over x squared minus 1. So yes, you can get some very funny shapes with these. Now, I'd like to do 2 more examples here. I'm going to start out real easy. So instead of asymptotes, we're going to have something different here. So let's say I have f of x equals x squared minus 1 all over x minus 1. So f of x equals x squared minus 1 over x minus 1. Well, it's true the degree of the numerator is greater than the degree of the denominator, and it's by exactly 1 degree. It looks like, okay, let's go for a slant asymptote. Well, but a lot of you, and rightfully so, are screaming, wait a second. X minus 1 divides perfectly into x squared minus 1. You're right. You're absolutely right. So it's true then that x squared minus 1 divided by x minus 1 equals the quantity of x plus 1 times the quantity of x minus 1 all over x minus 1. You would be correct. And you would even be correct in saying the x minus 1s cancel out. So you should literally be left with f of x equals x plus 1. That's partially correct. This is going to be a lot like graphing f of x equals x plus 1. And you're basically going to, except for one thing. Even if you get the fractions reduced down to just a simple polynomial, you still have to consider the original denominator. In the denominator, the function is not defined at x equals 1, right? You would have 0 in the denominator. So you still have to treat it as such, but you're not going to have a full-on asymptote. If you can ever cancel out the denominator, you still have a discontinuity at x equals 1, but instead of an asymptote, you're going to have what's called a removable discontinuity. At x equals 1. You have simply a removable discontinuity at x equals 1. So you're going to graph the line of f of x equals x plus 1, but when x equals 1 itself, it's discontinuous. So what that's going to look like is you put that x equals 1, put that f of 1 into this function. Well, 1 plus 1 is 2, right? So at the point 1, 2, you're going to draw an open dot, denoting that it's not defined at that point 1, 2, but it's defined to the right and left of it, but there is no asymptote. Really, you have no asymptotes. This is simply plotting lines. Alright, so when x is 2, you would get 3, right? X is 3, you get 4. X is 4, you get 5. x is 0, you should end up getting 1. X is negative 1, you get 0. X is negative 2, you get negative 1. You see the pattern. So what you're literally going to have is the line f of x equals x plus 1 with a removable discontinuity at x equals 1. And it's removable because we could then define the function at x equals 1. That's why it's called removable. And you see the shape of it. It almost looks like it goes into x equals 1, but it's not defined there. Which this is an interesting setup for when we get into Calc 1 when we're talking about limits and continuity. This really ties in heavily to it. We talk about removable discontinuities all the time in calculus. So this is kind of a cool setup for that. Now I'm going to do one more of the removable discontinuity type. Alright, let's do this. F of x equals x to the third minus 8 divided by x minus 2. So f of x equals x to the third minus 8 divided by x minus 2. Okay, well, the degree of the numerator is greater than the degree of the denominator, and it's greater than the degree by more than 1. So there's already no slant asymptote or horizontal asymptote, since the degree of the numerator is more than 1 degree greater than the denominator. And you notice that you have a difference of 2 cubes in the numerator, and x minus 2 just so happens to be a perfect factor of x cubed minus 8. So this x cubed minus 8 divided by x minus 2, it is true, it can be written as the quantity of x minus 2 quantity times x squared plus 2x plus 4 all over x minus 2, and the x minus 2's would cancel out. So really what this just turned into was a simple quadratic function of f of x equals x squared plus 2x plus 4, right? F of x equals x squared plus 2x plus 4. It turned into a simple quadratic that we're going to graph. However, let's go back to the original equation, right? The original equation, you would have had a vertical asymptote at x equals 2. It's still undefined when x is 2. But since you were able to cancel out the denominator, you have a removable discontinuity at x equals 2. Knowing that now, why don't we put in f of 2 and see what value we get? So f of 2 would give you what? That would give you 4 plus 4 plus 4, which would give you 12. Well, good news is it's off the charts, so you don't even have to worry about that. But at the point 212, you would put another hole there because it's not defined. Now, let's see. We know if we go to 3, it's definitely going to be even bigger than 12. So why don't we go to f of 1? Why don't we do f of 1 here? Well, that's just going to give you 1 plus 2 plus 4, which would give you 7. So when x is 1, y is 7. What about when x is 0? You would literally get 4. So at 0, you have 4. All right, there's your 0, 4. Now what about negative 1? So f of negative 1 is going to give you 1 minus 2 plus 4, which would give you a y value of 3. So at negative 1, you'll be up to 3. Now what about negative 2? So let's see, f of negative 2, you would get 4 minus 4 plus 4. So at negative 2, you'd be back to 4. Let's do negative 3. F of negative 3. So let's see, that would end up giving you 9 minus 6 plus 4, which would be 3 plus 4, that'd be 7. So at negative 3, you're all the way up to 7. And pretty much just go ahead and draw your merry little parabola, knowing that at the point 212, you have a removable discontinuity. So yes, you're going to get a parabola with a removable discontinuity at x equals 2, where the y coordinate's 12. So that's it for graphing rational functions entirely. In the very next lesson, we're going to get into multiplication and division of rational expressions, which for some of you will seem a lot like a review of Algebra 1, but it is very necessary. So I hope everyone has a great night. Take care.